Ever wondered how Google Maps works out which route you should take to avoid the traffic? Or how LinkedIn eerily knows to suggest that person you just met in the office earlier in the people you may know list? Or what about Amazon and how it thinks that it can make delivery via drones actually a thing? Today, we're going to talk about the algorithm that I use to find Bart Simpson's optimized trick-or-treating route around Springfield. But we're not doing it in C++. No, that's going. Back in October, I created the perfect trick-or-treating route for Bart Simpson that allowed him to maximise his candy gains while avoiding Sideshow Bob, using a combination of Dijkstra's and orienteering algorithms. And today, we're going to take a deep dive into the first one of these to get more of an understanding of exactly how it works. So to kick it off, let's talk about the algorithm that I struggle to spell as much as I struggle to say. Let's talk about the algorithm that can navigate its way around the London Tube map even more efficiently than I can. Let's talk about Dijkstra's algorithm. So my first encounter with Dijkstra's algorithm was actually in a further maths class at school, and I was confused. I didn't understand where we were by hand finding the shortest routes through some arbitrary graph, because it didn't really seem like the kind of maths that we should be doing in further math. Yes, I was that kind of nerd. So today I'm going to give you the context that I wish I'd had back then and talk to you about why we're actually doing this. So Dijkstra's algorithm is by definition a methodology for finding the shortest path between two nodes on a weighted graph, which when I put it that way is still really abstract. So actually let's start by talking about what some of these terms actually mean using something that I've now used for 4 videos in a row, the map of Springfield. So once again, here's the map of Springfield. I've already done a whole video on how I turn this beautiful artwork into something the computer can understand, so you can click up here to go and watch that. But for now, here's the setup. I've marked each character on the map and they're given by nodes. They're not the only nodes on the map, but they're the ones I care most about and make up the primary points on my graph. In order for a graph to become a graph though, we need edges, and those are given by the roads around Springfield. And this would be really easy if those roads just went directly between each character and connected them in a straight line. But much like in real life, Springfield is a city that doesn't work that way. So in order to capture the complexity, I needed to turn every single intersection into a node itself and then add the paths connecting them. I also added zero-weight connectors to make up for my lazy plotting of the character locations earlier. You'll be able to spot them because they look a whole lot less artistic, shall we say. By building up the whole graph, I have something that looks like this. As you can see from the graph, there are thousands of ways that I could get from Bart Simpson to his grandpa. Ones that make a lot of sense, ones that zigzag a little bit too much, all the way to ones that are massive detours that maybe even swing by the prison to go to Sideshow Bob. And that's a problem, because much like your commute to work, you probably want the shortest way to get there. That's where Dijkstra's comes in. So let me break down how this algorithm works. We start by creating a set of all nodes that we haven't visited yet, called the unvisited nodes. Creative, right? And then we set the distance to each of these nodes to be infinite, because we haven't found any paths yet, so we can't pick a shortest path there yet. The distance to the starting node is set as 0 because we're right there, we're just starting. We then look at the nodes that we're connected to from the unvisited set and choose where to go next. Typically, we want to choose the one with the shortest path, and in this case, starting from Bart, we're going to end up going to the end of the connector path because that has a path of 0. We then check whether we've arrived at our final destination and can terminate, or we haven't, which in this case, we haven't, so we keep going. Now for the current node, the one at the end of the connector. Let's say this is node A. We're going to look at all of its unvisited neighbours and see if it has a path there already stored. Let's call the one we're looking at node B. Now we check if we have a path from Bart to B already calculated. If we don't, great, we take our path Bart AB and we add it in there as the shortest path. But if we do, we have to make a decision. Say the path originally went Bart F K L J B. Then that might have a distance. If our distance Bart AB is shorter, then we're going to throw out that path and we're going to store our new path instead. Otherwise, if it's longer, we're going to keep that old path as the shortest path. After we've done this to every node connected to A, then we can consider A a fully visited node and remove it from the unvisited set. We don't need to go back there, we've done all the maths we need to do for it already. We continue these steps until we've completed node Abe Simpson and removed it from the unvisited set. At this point, we have whatever our path from Bart to Abe Simpson and whatever it goes by is the shortest path from Bart to Abe Simpson, and we've got what we set out to solve. So this is great. If I know the shortest distance between Bart to Abe Simpson, then I don't actually need all the other potential paths in there. I can just throw them out and use only the one that's the shortest. And even better, I can actually remove all of the intersections there and draw a straight line between the two of them, as long as I use the distance given by Dijkstra's algorithm. So if I do this for every single pair of characters in my Simpsons graph, I go from something that looks like a complete mess to something manageable and looks like this. But that didn't solve my trick-or-treating problem, did it? Because sure, Bart knows the fastest way to get to each character, but he might end up doubling back and therefore wasting time. And that still doesn't solve the problem that he doesn't actually want to go visit Sideshow Bob at the prison. It was here in my original video that I introduced the concept of penalties and rewards, literal tricks or treats that we could use to maximise Bart's candy collection. So much like how City Mapper gives you an alternative route when the Northern Line is down, we are going to use an orienteering algorithm to maximise Bart's candy collection all the way around Springfield. And if you want to save time while waiting for your code to run, we have built a platform designed by data scientists for data scientists to absolutely decimate that wait time through intelligent caching, multi-threading, and the ability to spot those bugs that you really wish you'd known about before you sent 2.3 million rows of data through the code. We're launching a closed beta next month, so you can sign up to be part of it via the link in the description. Oh, and before you go, there's a massive penalty incurred if you don't hit that like and subscribe button below, so you probably best do that, and maybe there's a reward in it for you too.